Hello, this presentation is titled Geographics Data in Raku Demo. My name is Anton Antonov. Today is June 16th, 2024. This presentation is mostly about these two Raku packages, Data Geographics and JavaScript Google Charts. You can see here in this plot the data from the first has been used, and I have invoked a function from the second package to make this geographical plot. So before going further, I would like to mention that there are three panels I'm going to be using for this presentation. The leftmost panel is with a mind map, which is going to get us oriented where we are at, and I'm going to use it to summarize the presentation. In the middle is the presentation itself, and to the rightmost panel there is a browser with which I'm going to show some relevant data. Alright, so what is this about? Looking at the mind map, the Data Geographics package is the protagonist of this presentation. It has country data and city data. Visualization in Geographics and in data science in particular, which I kind of specialize, is very important. So initially I wrote this presentation with JavaScript D3, but it was difficult for me to make geographical plots with JavaScript D3. I'm not saying it's impossible, it is possible. It was much easier it seemed, and it is actually in practice, to program this Raku package, JavaScript Google Charts, which interfaces to Google Charts. Google Charts is a relatively old framework for making pre-canned types of charts, like you can see them here. D3GS which is used in JavaScript D3. D3GS is another JavaScript library for graphics, but it's a lower level and it's much more flexible, and you can do a variety of plots. So so the presentation is using JavaScript Google Charts. The package DSL Entity Geographics is going to be demonstrated very briefly. Actually, we can do named entity recognition with it, and say if you make conversational agents and you want to recognize city names or country names, you can use this package. This package, DSL Entity Geographics, is very closely related to Data Geographics, but they're independent right now. Data Geographics is a little bit too big. I'm going to explain that. And I need to figure out how to make it smaller, how to make the data in it smaller, and to make it more shareable. Then I'll introduce more dependencies based on Data Geographics. So we're going to see countries data, some kind of rudimentary analysis with, say, linear regression over the gross domestic product and electricity production. The package Data Geographics has also cities data, and I'm going to be showing some related statistics. Again, probably a very convenient way to showcase the charts in JavaScript Google Charts. I'm also going to use this package DSL English data query workflows, which allows for generation of code. This is a minor point. And with the city data, we're going to do some nearest neighbors graphs. We're going to do some proximity search. I'm going to be using another new package called MathNearest. So MathNearest, MathFitting, JavaScript Google Charts, they're very new packages. Within a week or two, they have been proclaimed in the Raku ecosystem. Alright, so with the presentation here, I was discussing already D3GS versus Google Charts. I'm not sure, should I go further here with that? Probably not. Google Charts, well, Google Charts is an old package, it's like 10 years old, same with D3GS, but Google Charts, since it is pre-canned and it has extensive documentation, like for example, if I take this bar charts here, right, and if I look at, say, the parameters which it has, so quite a lot of parameters, very well documented, relatively old, at least 10 years old. So this makes it a very good target, so to speak, for large language models. So large language models should be extensively trained, in a sense, with discussions or documents or whatever, right, about Google Charts. And it is the case. I'm actually here, I'm making a specific prompt, which or persona, if you will, LLM persona, with using some of the most recent models of ChatGPT. And so here I'm going to request certain elements. For example, how do you do tuning of certain plots? Like, say, in this plot here, we can see that, the countries which are known by data geographics are in some shades of green, and in gray are the rest of the countries. But how exactly do you tune those colors, right? So figuring out is it background, is it just background color, right? So it's like, for example, the dataless regions, which are in gray, right? So these are the ones which the package doesn't know about. Again, I didn't necessarily know the names of these options. And so this, you can see, we get the result here. Because I did say that I want the result of the options to be as Raku code, it did put the large language model, it did put this code fences Raku here. But otherwise, this is JavaScript, right? All right, so let's actually demonstrate something else. You can tell me, well, but why use Raku at all for this? Can you just generate plots directly? Yes, we can. This is exactly what happened here. I did say that I want some. Let me show you what the result is. So automatically, when I have this large language model chat cells in a Raku chat book, automatically the output is being copied in the clipboard. That's why I was able to just put the output above. I was able to put it here. And so yeah, we can see that this is the Google Charts type of framework, right? So we have a geo chart and so forth, right? And the countries, they have been colored between green and orange, exactly what I requested here. And I asked for the div Cuba to be used and so forth. So this Raku chatbook is using the Jupyter framework. The Jupyter framework is based on browser technology, and so that's why we can visualize this kind of outputs easily, in a Jupyter notebook. And all right, I'm going to continue further with the presentation. So I'm going to be discussing countries and what kind of metadata we have for them. As I mentioned, the package data geographics is a little bit too large right now. It's around 30 megabytes with all of the data I have for countries and cities. I want to figure out how to make it smaller, and what kind of ways we can make the data imprint smaller. If it is not possible, then, well, some other steps need to be taken. But for now, I have 29 countries, so you can see these are like, say, each column has 10 countries except the last one, so 29 countries. For each of these 29 countries, I have approximately 200 metadata points. Not metadata. The metadata here for these countries is being shown. They're approximately 200, I think 195. And so, just to demonstrate what kind of a smaller data set, right, a subset of this 195 data points, I have made this table. We have the name, the full native name, ISO name, area, population, gross domestic product, and electricity production. So I'm using camel case, and it's just not convenient to use the Raku kebab case for this kind of data, or at least for me it seems very unnatural. Also in Google Charts you can see, it's not me who is imposing this. They do use the camel case, so I'm sticking with the camel case for the geographical data. So this data here, I'm going to use these two last columns and make a correlation plot. So you can see it here. So we have this we have plotted here the GDP in the X and the electricity production on the Y, and you can see this is a logarithmic it's a logarithmic scale. If I put here, if I disable the logarithmic scale, this plot becomes very uninformative because China and USA dominate the whole plot, and all of the other data points are in the left bottom corner. And here, though, with this plot, I can show that I can show trend lines, right? I can fit this regression line. This is coming as a functionality, built-in functionality in Google Charts. Now, if I make this logarithmic scale, and I think, let me see, if I make it logarithmic scale, this might still work, at least to a point, maybe not with all of them, right? Okay, yeah, so it works, you know, if it works if I make one of them logarithmic, more precisely if I make the H scale logarithmic. If I make both of them logarithmic, I do not get, both logarithmic, I do not get this, what I expect here. So not necessarily a great motivation, but a motivation nevertheless. Let's use this property or this inability to make the fitting in the logarithmic plots, to make the fitting line. Let's use that as a motivation to make our own fitting. So here I'm using this new package math fitting, which can do, at this point it can do linear regression only in 2 dimensions, or the regressor variable is 1-dimensional, the regressant is also 1-dimensional. I'm going to extend it very soon further to be multidimensional. Anyway, so here we get linear model fit. It's an object, and this object, it's an object which is also callable, and you can see I can call it with certain parameters, get the parameters here, do some summary. We see that the summary is actually not of the summaries of the residuals. So this object also knows the residuals of the approximation. And if I plot these residuals, if you follow here the 0 axis, you can see that they look like white noise in a sense. And this means that we have a good fit, which is not a big surprise if you just look at the logarithmic plot. And so let me redo it here. If you look at the logarithmic plot, right, it's a very nice, obvious, very nice line, which is here. Maybe we have a couple of outliers like Iran and Denmark and Botswana, but in general, it's like a very, very tight kind of rectangle around, obviously, some kind of line. It can be fit easily through it, or faithfully. And so this is what is happening here. I have used this functor. I have added this column fit to the data, and here I'm actually making a combination chart, and I'm saying that my plot is a scatter plot, but treat the series with index 1, treat it as a line. And so what happens here is that when you have this combo charts in Google Charts, the first column, in this case GDP, this is just what is on your X. Electricity production has index 0. This is your first Y column, and then the second one is fit. And of course, we are using indexing from 0, so that's why I need to say series 1. And so this is what you see. We are basically plotting the fit, and we have this kind of nice kind of looking fit. All right, so there's some other data, which country data, which is being put into the package, and as I said, nearly 200 data points. So what you see here, it's basically contours, right? Contours, which is a contour plot, is being made for the coordinates of the boundary of a certain country, United States. So this is what you see here. Country data, United States, I have extracted it, and then get the coordinates. So this is an hierarchical kind of structure. It's a hash map of hash maps, and so I can retrieve different data from it. Now, I can do this kind of plots with D3GS. So you can see here, if I find this, yeah, I can do that. But actually doing geographical plots like the one I was showing in the opening here, it's not that easy, at least for me, with D3GS to figure out what to do and how to do it. And it was fairly easy to have fairly good results using Google Charts fairly quickly using with Raku. Raku, though, is just a conduit, so to speak, to Google Charts. I'm not trying to put my own options, so I kind of accommodate some more common type of inputs, like say single dimensional list of one-dimensional list of numbers. I can still plot it, which is not necessarily allowed by Google Charts, but in general there's not much kind of change in the way Google Charts work. With this package D3GS, when I use it in Raku, I mean, this is definitely a certain opinionated use, so to speak, of D3GS. So yes, I'm using the underlying functionalities, but I'm kind of designing my own type of interface, which I think should be, at least to a point, appealing to generic Raku users. All right, so let's continue with the city data. So city data, it's not that populated with different types of data points. It has locations, populations. Actually, it has also links, and this is something fun to show. So here you can see I have 32,000, 33,000 cities from United States. I filtered them here. So I took the city data. It's a hash map of arrays of hash maps. Here you can see from this data set, city data, I have extracted 7-8 columns, ID, the country, the state, the city, the population, latitude, longitude, elevation, and location link. I think this is the only data I have for the cities. Now the location link is kind of nice because we can visualize it with Google, right? So we can, if I click on this location links, I can go to the browser and see where this is. And so I had to work, so to speak, for it a little bit. I had to replace in this HTML table, which is being made with this function, to HTML, which is, you know, coming by default, so to speak, if you use Raku Chatbook. Yeah, I had to replace the texts or text substrings that look like URLs. I had to replace them with this syntax from HTML for links, but yeah, that was very convenient. Let's pick some bigger city here. Let me actually see, can we get some bigger city with a larger population? And I don't see very large populations yet, maybe 25,000. No, let's pick this one. So yeah, I mean, okay. It's kind of nice, kind of convenient to have this visualization. I'm not sure is it possible to visualize this type of charts directly here in the Jupyter Chatbook. Probably that's possible. It's not something I'm very interested to do it. It's just not something it's a high priority, and I haven't investigated it that much. All right, so we're going to look into the distributions of across the states of population and number of cities. And in order to do that, I have to actually aggregate the data. So my data here, and go back to this mind map, I only have countries data as an entity, right? I have an entity as a countries, and I have another entity, cities. Yes, cities do refer to states, but there is no separate entity state for which I aggregate or accumulate or have specific information. Maybe I should have, but at this point I don't. So in order to see, for example, some interesting analysis or exploratory analysis of the distributions of the populations and the number of cities per state in the United States, I need to do something like this, right? I'm basically taking this city data, I'm grouping by state, and I am finding the the number of the cities in each state, and I'm summing the population. This is what is happening here. When I say summarize population, what you see here, this generates this Raku code, which tells me that the column population from the dataset is going to be summarized with the function lms min and max. I have replaced min and max with sum, and we get what I just said, right? We get for each state, we get the number of cities, because population is per city, right? So if I find the number of elements of the population elements, right, in the column population, if I find the number of elements, this is going to give me the number of the cities, and then the sum, of course, is the population itself. And so here I'm basically doing this and more or less just preparing the data for plotting. And sometimes with Google Charts, you need to spend some time to massage the columns in order to get, say, like the tooltips I want to get here. So I am getting the tooltips I want, but I had to somewhat work for it too hard. Now, in some of the Google Charts tooltips, they come by default, but they didn't have this default here, didn't have the form I wanted. And you can see here, for example, for Illinois, I want it to be Illinois in bold, and I have certain format for the tooltip. It is definitely possible. It's it's just we need to basically look into the documentation and see the examples, and then something like this can be made. Now you can see I'm having logarithmic plot again, but it's not on both scales. It's only on the horizontal scale. And what does this mean? So if I do this again, so actually I don't want to have logarithmic scales. Apologies. So it is actually on the vertical axis, the logarithmic scale. It should be, right? Because right now you can see some kind of exponential dependency here, but it's also becoming very spread out and so forth, right? So if I logarithmize the x-axis, what is going to happen? Right, it's not informative at all. And if I logarithmize the populations, then we start to have something like, I mean, it's not exactly linear, but it is somewhat of a rectangular shape. So it is a linear dependence here. I can claim it's a linear dependence here with a large dispersion. So this is something to be expected. This means that the population, it has some exponential dependency when it comes to the number of cities, and makes sense. The more cities you have in a state, the more likely there'll be cities which are with much more citizens, in them. So basically large cities. And so that's why we get this. This can be done, this can be illustrated in some other way. For example, here I have just plotted the number of cities. Now we're going to look into the Pareto statistic. So this here is, so here you can see this is, say, New York, whatever, right? Pennsylvania, whatever. And so I have the numbers here. So I want to make the so-called Pareto principle plot, or Pareto principle adherence verification with the suitable plot. What happens here is that I have sorted the cities according to the states according to the number of cities they have. Then I accumulate those numbers here progressively, and I normalize by the total. And so this is what the Pareto statistic is, 80-20 rule, if you will. So here we can see that I have done this both for populations and for number of cities. So we can see that, say, what is this, approximately 30% of the states have 60% of the cities. And similarly, approximately what, like, say, 20% of the states have 60% of the population. I mean, the 80-20 rule is actually in a different manner displayed here. So this is more, this is like like 40% of the states have 80% of the populations. All right, yeah, fair enough, whatever. This can be done in a slightly different way. I don't need to show it here. It's just different styling. In case you use this notebook to do charts, you might look into this alternative representation. All right, so this here I'm going to move to actually doing proximity searches and using this new package MapNearest. So here I'm taking again this city data. I have filtered it in some way. There are some outliers, I think, just to make the data kind of smaller, to get this more familiar way of visualizing QSA. So what is happening here? I mean, I have made the plot data, but before going to the plotting, what I'm extracting, I'm making a map or a hash of the ID of each city with its geolocation, latitude and longitude. Now I'm making this nearest, I'm calling this function nearest, which makes a functor, right? It's another functor. It makes this function object with the distance function geodistance, and over this locations. And here I'm basically trying to I want to use this function to find the nearest neighbors of Las Vegas. Las Vegas, you know, the Raku and Pearl conference is happening, I think, this month in Las Vegas. So that's why we're using Las Vegas here. So there's an alternative way to find this ID. It's this is the entity name recognition, and I think, you know, this is actually I'm going to return to that. Let's actually continue with the nearest neighbors. So here I'm finding the actual nearest neighbors with within 100 kilometers. So the geodistance function, this one here, by default uses meters. Geodistance is a function which comes from data geographics. So here I'm going to use the opportunity to mention some of the other geographical packages in the Raku ecosystem. I'm mostly familiar with GeoBasic, which is very new actually, and well-known text. So GeoBasic has also distances, right? And so, but Geographics, data Geographics has also geographical distance because, well, why not? And I'm using this geodistance is from the package data Geographics. I'm using the Haversine formula, which is maybe not that precise, but it's considered to be a very good approximation. So so this functor, right, NF, I can use it to find nearest neighbors. And I have found the nearest neighbors here, and here I'm just preparing my search point, so to speak, and the found nearest neighbors and all of the cities which have more than 1,000 citizens. Okay, just a moment. So this is the plot, but so here when I make this here, you see I'm picking from the set of 33,000 cities from USA. I'm picking the ones which have population more than 1,000, and so this is how this plot looks like. So if I go here, right, so this here should be Las Vegas, right? So this red point, the points in yellow, these are the nearest neighbors within, say, 100 kilometers. I'm going to show how this 100 if you want to use miles, right, we can use something else. You can see here there are a couple of signatures to be used when you use this nearest neighbor function. In this particular case, the second argument has a list of 2 elements. Whatever this means, whatever number of neighbors you have within 100 kilometers. So the most straightforward way to call that would have been to just say that I want the top 20 neighbors or something like that. All right, so before actually going further with the nearest neighbor graphs, I wanted to discuss the IDs and the name entity recognition. So I did mention here that I can have this name entity recognition in this way. This function is provided by DSL entity Geographics, and it has some nice properties, I would say. For example, if you say Atlanta, it's not going to give you an ID like this because Atlanta is a generic name. But if I say United States, then there are more than one Atlantas in United States. So if I say that I want exhaustive match, then I'm going to get a bunch of Atlantas being matched across USA. So yeah. And all right, I guess that was it for the name entity recognition. So let's move to the nearest neighbor graphs. This is very interesting application, of course, to the nearest functionalities in math nearest. So here you can see that I am actually picking certain states. I want to reduce the search space, but I have picked states, cities in Nevada, which have more than 30,000 citizens. Again, I'm taking an ID, a pairs from the identifier of those cities to their geo-coordinates. And then I'm kind of reducing the label sizes and basically replacing this United States, right? United States, Nevada, whatever we saw here. I'm replacing it with an empty string, right? So this is what is happening here. Then I'm calling the function nearest neighbor graph, and I'm asking the format to be given into Mermaid. Mermaid is a type of formalism for specifying graphs and diagrams, and then I can visualize this. I can visualize this graph in this Jupyter notebook using the package www.mermaid inc. So it's a service, web service, right? Mermaid inc, which this package provides access to. So the alternative here, and since I mentioned that I'm using D3GS, let me see. I should have. I mean, I have everything I said. I've presented so far. It's also written in JavaScript with JavaScript D3, right? Using D3GS. So you can see here, like this is Las Vegas, and this is the search point, and the tooltip is not on top of the chart, but it's actually here at the bottom. You'll see it at the bottom of the screen. All right, so the graphs themselves, I can actually use the D3GS graphs, the so-called force graphs. It's very nice, very interesting. If let me see, I think this is, I already executed. Yeah, so there's some kind of settings for this force or whatever, but the nearest neighbors, nearest neighbors graph, can be set in such a way that to look somewhat like this. If I say remove some of these default parameters I put, this might look somewhat much less appealing, for example, or or whatever, right? But yeah, I'm not going to go further with that. I'm just saying that this is graph plot type of visualization. This graph plot is in Raku, right? So it comes with the Raku. I don't need to go to an external service for it. This is what I'm doing with Mermaid Inc, right? With Mermaid Inc, when I'm here, this actually goes to, you need to have a web connection. It goes to an external web service to make these graphs. And here I have made the graph, instead of taking the top, the closest neighbor to make the graph here, I can take all of the neighbors which are within radius of 8 miles. And so this is what I was saying. If I want the distance function to be something else, not to be using the units meters, I can define it in this way. I can say that I want the distance function to be within miles. And if we want to convince ourselves that we get meaningful results, we can make this cross tabulation. I can make this Cartesian product of the locations, find the geodistances. It basically make this kind of this table. You can see on the diagonal they're all zeros. So basically the columns correspond to the rows, and so these are the distances between the different cities. So I do have some future plans for this. Quite a lot of this probably needs to be upgraded in some way. I'm not going to discuss this too much, but some of my future plans about JavaScript D3 they become much lower priority because I have Google Charts. I have this access to Google Charts. I want to mention something else here, since I did let me see, some of the things I can not do with charts. First, about the graphs, I don't think you can plot this kind of graphs. Maybe you can if you use the maps functionalities, but you need to have Google Maps API key. So they do have some kind of nicer functionalities here, but you need to have the key for it, as far as I can tell. And I haven't seen actual graphs being plotted. So maybe I haven't looked hard enough. Some of the things I can do here, which are more specialized, and they don't necessarily come from the free.js, right? But I have done it, so I'm going to demonstrate this kind of one of my favorite examples, to be honest. So actually, it's not graph plot; it's random mandala. And so this is just not easy to do. Just not easy to do with Google Charts, right? But you know, I could figure out how to use the free.js to make this kind of plots. So I mean, I'm going to return to the top image here. So in summary, I would say you know, we considered all of these elements I put into the mind map. So yeah, data geographics, it has countries data, it has cities data. With some additional packages, we can do some statistical analysis, maybe rudimentary, maybe not so rudimentary, but it's very informative. All of these fittings and distributions we plotted, and we can make informative plots over this Geographics data using both of these packages, JavaScript D3 and JavaScript Google Charts. All right, thank you for your attention.